So, I think we will now continue with the Hartree-Fock equation. I hope all of you by now should be able to write the Hartree-Fock equation in non-canonical form, right? Canonicalization we will do, but non-canonical form. Can you all write? Okay, good. So, what is the first term? H of 1, right? And chi I of 1. Then what is the next term? Sum over j integral chi I star. Will it be chi I star? Chi j star. Okay. And the coordinate 2. Then 1 by R12. If you want, we can put the exchange together, right? This is a very nice way of doing. Actually, just put 1 minus P12. Your problem is over as far as the equation is concerned. Okay? Into chi I1. So, let me write this as sum over j lambda ij chi j of 1. As I said, this can be made lambda ji or ij, it does not matter, because that depends on how you start with. So, this is your Hartree-Fock equation in a non-canonical form. So, anybody asked, you should be able to write this, very simple. So, you have a Coulomb term which comes from the density of the electron 2 in chi j, and you are summing over j, which means you are taking the interaction over all the electrons. So, when I am integrating over g tau 2 chi j star chi j with 1 by R12, you get effective one particle interaction on the electron sitting in a chi I orbital. That is the interpretation of the classical term. Of course, the exchange term, it is not easy to interpret, because when I actually allow P1 to act, this goes out of the integration and chi I comes inside the integration. So, that is the reason we can't now call it an exchange. And we saw yesterday in the DFT also that similar things are there, that the exchange is difficult to integrate. Okay. So, in fact, DFT class is very much on the same thing, those who are attending this. Anyway, so we call this density. This sum over j chi j star 2 chi j 2 is actually density of the electron 2, right. So, this is the density of all the electrons interacting via 1 by R12. So, density is nothing but probability. So, this is the weighted average. So, this is why it is called weighted average, because weighted average is probability into the actual value. So, weighted average into 1 by R12. That is how this electrostatic Coulomb term is interpreted. The exchange term, of course, cannot be interpreted like that, but chi I will become 2, chi j will come outside 1, and this part is of course a non-canonical form. So, I do not yet have an eigenvalue equation. Okay. And this is basically the HF equation for all the spin orbitals. Okay. So, I get, if I solve this one particle equation, I will get chi I, and then I can construct my wave function using this chi I as chi 1, chi 2, etc. to chi n. So, the question is of course which n spin orbitals you choose. So, these are my Hartree-Fock determinant. So, initially if you remember, we are using tilde because it is a trial function. Now, I want to tell you that we will drop the tilde, because now it is no longer a variational or trial spin orbital. These are the spin orbitals which come out of the result of the variation. So, now we will say that this, we will drop the tilde, we will say these are the Hartree-Fock spin orbitals. The one important thing we noted is that this operator, Hartree-Fock operator, which we called F, the entire operator, includes this Coulomb and exchange term, which is basically dependent on the spin orbital themselves. So, to solve this equation, you have to use what is called the self-consistent field procedure. Okay, we discussed that last time. So, you have to solve in an iterative manner, and this is the origin of this term SCF. But because it is solved in the self-consistent manner, this procedure is also called SCF procedure. Okay. So, whether non-canonical or canonical, that is exactly the same. So, this is basically the Hartree-Fock equation for one particle spin orbitals. Note that this entire term that has really come out of the variation method, that I wanted to ensure that the energy E Hartree-Fock, which is psi Hartree-Fock, H psi Hartree-Fock, is now minimum. Okay, is now a minimum. So, we have ensured that this is minimum for all single determinants, right? We have ensured that this is a minimum for all single determinants. If I choose all possible single determinant, this particular spin or determinant which satisfies this equation is the minimum energy. So, that is what we wanted. Okay. So, we will go to the further part of how to canonicalize and then do lots of interpretations. Before we canonicalize, let me talk about an effect of unitary transformation on this equation. All of you know what is unitary matrices, right? So, effect of unitary transformation on this matrix. So, let us assume that I transform the spin orbitals by a unitary matrix. So, let us say that I get a new set of spin orbitals which I call now prime, chi prime, after I reach the Hartree-Fock equation. Okay, I transform them through some chi j of I, or sorry, some uj of I chi j. So, what I am doing essentially is that I am making a transformation. I hope all of you understand what is a transformation. It means that the new set of spin orbitals are linear combination of the old set. Of course, I can always do that. So, I am choosing the new orbitals which are a function of the old set, linear combination of the old set. The combination coefficients are what I am calling as a matrix which is now unitary. So, this U is a unitary matrix. Alright, these coefficients I can put them as a matrix, and this is a unitary matrix. Of course, you know what is a unitary matrix. If I take adjoint EU dagger or EU dagger U, that is equal to identity. So, let us assume that we transform these spin orbitals by unitary matrix. So, what will happen to the first thing, what will happen to the orthonormality of the spin orbitals? Okay, can somebody tell me? The original spin orbitals were orthonormal, because that was the condition, if you remember, we put while solving the Hartree-Fock equation. Now, I am doing a unitary transformation. So, will the new spin orbitals remain orthonormal or will not remain orthonormal? Remain orthonormal, right? All of you can prove this if I ask. So, can you show by this equation that chi I prime, chi j prime is also delta I j? Okay. So, how will you prove? What is the strategy? You will expand this side, you will expand this side as a conjugate of this, expand the right side as it is, and then show by the fact that U dagger is identity, this results into delta H. I hope all of you can do this. It's a very small home exercise. So, basically you have to do the summation, but it actually teaches you a little bit of an algebra, how to manipulate the summations. So, for example, when I write this, what do I get? So, remember, when I do expansion of chi I prime, I have to bring in another dummy variable. It cannot be I or j, right? Because they are specific index. So, what is the dummy variable I will bring? Let us say k. Okay. And what will be now chi I star? It will become chi j, chi k, sorry, it will become chi k, because now I am expanding chi I prime with the dummy variable k. So, this will become chi k and you will have u k I, right, star. So I am just going to piece it together. And then you have chi j prime, which I again expand by another dummy variable, let us say L. So this will now become chi L, right? And this will now become U L J. Remember, don't get confused with this, because now this is J, this is a dummy variable L. So everything will change accordingly. So this will become U L J chi L. Correct? So this chi L has come here, and this is the combination coefficient. So for each given I and j, I can write chi I prime, chi j prime by summation like this. Now can we manipulate this? You have UKI star ULJ. Right, you change one of them to be adjoint. So for example, if I change this to be adjoint, you become U dagger ikth element, right? And this remains as ljth element. So what? How do you do that now? How do you bring U dagger? Okay, so okay, sum over KL. So this is already delta KL. So you want to say this is U dagger IK, good. Then you have delta KL, good. Then you have LJ. So I just shifted this here. Huh? Yes. So because of delta KL, that's okay. So either way, if you write, it is a product of U dagger identity U matrix, which is still U dagger U. So it's an identity matrix. Correct? So identity matrix ijth element. So it's a delta ij. This can be seen in many ways, or you can simply say k is equal to L. So you can see it from that way, U ik, U kj. Sum over k, that is delta ij. So anyway, this actually turns out to be nothing but delta. Okay, so that is what we wanted to show. If you do not bring the delta KL, it may become complicated, because you have U ik dagger and U JL, and then you can't do anything. So this part is very important. To recognize that this part I can bring it inside, or at least recognize this and make k equal to L. Then it does not matter. Then you can directly do it there. So either way, the physics is the same. But if you just want to put mathematics, you can simply put delta here. Delta KL is nothing but identity KL. So you can say U dagger. Then now you see it's a repeated summation. K is here, K is here, L is here, L is here. So it is U dagger identity U, which is same as U dagger U, which is delta I. So either way, you should be able to do this. Is it clear? Is it clear to everybody? These manipulations are very important. If you get confused with manipulation, you will not get the results. Matrix manipulations, you must learn. All right. So this is a very important thing we learned, that if I do a unitary transformation on the spin orbitals, the resulting spin orbitals remain orthonormal. So that's a good comfort, because when we derived this equation, you remember we wanted that the orthonormality should be preserved. Otherwise, the determinant will not be normalized unity. Remember, when I write E Hartree-Fock, I have not written the denominator. That is only because these spin orbitals are orthonormal. So if I do a unitary transformation, I want to write the Hartree-Fock in the new basis. I must ensure that the new basis of spin orbitals remain orthonormal. So that is, in fact, this is a very general property of unitary transformation, that if I have a set of vectors and I transform this set of vectors by unitary transformation, the new set of vectors, if you start from an orthonormal set, the new set also remains orthonormal. So two orthonormal vectors can always be connected by unitary transformation. So remember, there is no unique orthonormal vectors. I have one set of orthonormal vectors, I can go to another set of orthonormal vectors, another set of orthonormal vectors, and so on, each of which is connected by unitary transformation. And product of two transformation, unitary transformation is also unitary transformation. I hope you know that. If I have a two transformation U1, U2, right? So I transform one set to one, original set to a set 1, or 0 to 1, 1 to 2. Then of course I can go from 0 to 2 also by another transformation directly. And that would be simply product of U1, U2. So if each of this is unitary, the product is also unitary. I think all this you should be able to prove in metrics Okay. So, the unitary transformation is very, very important in physics because it preserves the orthonormality. That is a very important part of a vector space, and this has been used in physics many times. Okay. So, that is one thing. I just showed this, but this is very general proof. It has nothing to do with Hartree-Fock, this part. Take any set of vectors, do this transformation, it remains orthonormal. So, now let us see what happens if I do a transformation here. If I do the transformation here, the entire equation will change because everywhere chi will become chi prime. Correct? Wherever there is a chi, it will become chi prime. So, I would like to know what happens to this equation. Will the operator, which is the Fock operator that I have defined, will it change? Remember, in the Fock operator, there are three terms. I am again repeating. One is the one electron part, which is the kinetic and one electron, whatever external potential, electron nuclei, any other external potential. The second is a Coulomb part, and the third is the exchange part. So, there are three parts of the operator. Each of them is an operator, and I think it is good to write this as an operator form. So, I have already defined the operator. So, let me define the operator again. F, I defined F in the original basis. So, what is my F? I am writing it F as H. So, F of 1 as H of 1 plus sum over J, and I call it a Coulomb operator, Jj of 1 minus sum over J, Kj of 1. So, let me say that let me write it in this manner. Can you identify Jj and Kj? So, what is Jj now? This is a Coulomb operator. It is an operator now. Coulomb integral you have already written. That is for the entire energy. But here only d tau 2 is integrated. So, this part is only an operator, function of 1. So, I am only talking of this part, which will actually act on chi I 1. So, what will be Jj of 1, Jj of 2, or Jj of 1, sorry. So, this is integral chi j star 2, 1 by R12 chi j 2 d tau. Note that this is now an operator because it is an incomplete integration. It is a function of electron coordinate 1. The same way I can write Kj of 1 as integral chi j star 2, 1 by R12 P12 chi j 2, because otherwise it is very complicated to write. Because if you actually try to write, then this will become chi I2, it is very complicated because you are writing the exchange due to the spin orbital chi j and suddenly some I will come. So, formal way to write is just put P12. That's all. So, just change this 2 electron part for the exchange. It is no longer 1 by R12, assume it is 1 by R12 P12. So, the exchange part itself has a permutation. So, then you can write Jj minus Kj, and F can be then trivially written like this, and your equation, Hartree-Fock equation, then becomes F of 1 chi I of 1 is sum over J epsilon ij chi j of 2. Again, I repeat, this can be epsilon ij or epsilon ji, and according to convenience you can choose that. So, this is your Hartree-Fock equation, if you remember. So, I am rewriting this F operator by introducing what I call the Coulomb operator. So, this is called the Coulomb operator, and this is the exchange operator. Just like we have Coulomb energy and exchange energy, so we said now it is a Coulomb operator and exchange operator in the Hartree-Fock operator. So, now when I am doing the unitary transformation, I have to see what happens to the operator. It is very clear that the H will not change. Okay? With operator will remain the same. Of course, chi I will become chi I prime, but as far as the operator is concerned, it will not change because H does not depend on spin orbitals. Correct? I am only changing the spin orbital. What will change is the Jj and the Kj. So, we have to see how does this part, not each Jj, but the sum over Jj and sum over Kj change. If I change the chi j to chi j prime. So, that is what we will do now. So, let us take the sum over J, the Coulomb operators for each of these spin orbitals. And now again we do exactly the same. So, sum over J Jj of 1. So that is what we are doing. So you have the Jj there. So what will be the result? Jj of 1 prime. Prime because now I am writing it in the new basis. So what is the result? It will become chi j prime star prime 2, right? 1 by R1 2 chi j prime 2 d tau. Right? So everything I am just writing in terms of the new spin orbitals. That's all. There is no difference. Then what I will do? I will apply the fact that the new spin orbitals are unitary transformation of the old spin orbitals. Right? So exactly in the same manner I will do. So I have to write chi j star prime 2. So now we can write this. To write this, what do? I will bring in the new dummy index. So again remember, chi I was sum over j uji chi j. So now what I am going to write is chi j star 2. So let's bring in a dummy index k. So like there is a sum over j. So sum over j is already here. Now I bring in a dummy index k to expand this. So when I bring in the dummy index k, this becomes k. So it becomes uk and this is now j. So it becomes ukj chi k, right? So it is ukj star chi k. I hope all of you can see this, how to do the manipulation of the dummy indices. Then you have 1 by R12. So now you have 1 by R12, which will come in the integral, which will not change. Then the next is chi j prime 2. Although this is also j, I have to re-expand this. So to re-expand this, I have to bring in a sum over L. And now I am going to write chi j prime with a sum over L. So it will become u Lj chi L. So u Lj and this will become chi L. Or I can write in the same manner integral. Let me write in the same manner that we are used to. Chi I star 2 1 by R12 chi L d tau. Please make sure that you understand this. So what I have done for j on the left, I have brought in a dummy index k. For the j on the right, I have brought in a dummy index L. And I am writing this as the old spin orbitals. Note that this is the old operator. Okay? If I sum properly when these are equal. So that is important. Right now I can't associate because this k and L are different. If you look at the operator jj, it has both of them identical. So let's see how to manipulate now. So now again we do the same strategy. First we bring k and L outside, j inside. So first I am summing over j. When I sum over j, you note that the j occurs only here. J does not occur here now. So I am going to sum this up over j first, but while summing, I will again do the same strategy of changing the u dagger. So it will become now u dagger, or rather u Lj u dagger jk. So I just push this on the right of this because they are all commutative. They are all numbers. So I am now writing this as first u Lj, then u dagger jk. Then the rest chi k star 2 1 by R12 chi L2. Note that these are the old spin orbitals. This was the new spin orbitals. I have expanded them to the old spin orbital. Okay. Now, moment you write it in this form, you can see the sum over j can be trivially performed. Repeated index. So this becomes u dagger Lk, which is nothing but delta Lk. Correct? So now I write this. So then this becomes sum over KL delta KL, because the sum over j is performed over this, and you have phi k star 2. Now you can already see the result that you want. Delta KL phi k star 2 1 by R12 phi L2 d tau 2. Correct? alright, sum over KL. Of course, since delta KL is there, K is equal to L. So, this is nothing but sum over K JK. Because now K and L are equal. So, since K and L are equal, this becomes phi K star 2, 1 by R on 2 phi K 2. I mean, I can write this L here. Sorry. So, eventually L and K are equal. So, this becomes JK2, JK1, sum over K. So, I can write that this is same as this. So, what I have proved, if I start with the new spin orbitals and sum over all the Coulomb operators with the new spin orbitals, that is same as the sum of the all Coulomb operators in the old spin orbitals. Is it clear? That means in the Fock operator, the term, this term also does not change. It remains invariant. This term anyway does not change. This term remains invariant because the summation over this in the old is nothing but summation over this in the new. Don't worry about this J and that K, because that's a dummy variable. Okay? But basically the dummy variable means that you are taking all Coulomb operators over all spin orbitals. In the new basis, you are taking sum over all Coulomb operators in the old basis. So they are identical. That means this part of the Fock operator is identical. Is it okay? I can go run through it again. So how did I prove this? I started from the sum of the Coulomb operator in the new basis. So I plug in the expression of the Coulomb operator, except that the chi's became new basis, chi j star 2, etc., etc. So that is a sum over J. Then I did each of the new bases expanded in the old basis, and I brought in the unitary matrix for chi j star 2 here, chi j prime star 2 on the left, chi j prime 2 on the right, and introduce two dummy indices K and L. So then I get this expression. The rest of the expression will remain same. So 1 by R12, only here chi K2 and chi L2 will come. Then I said, let us sum over J first. So I just interchange these two summation, summed over J first, and that is nothing but delta KL or delta LK into this. So that is what I got. So J is now over, so it's only sum over KL, and then since K is equal to L, this is nothing but sum over KJK or sum over LJL. It doesn't matter. K is equal to L. So all Coulomb operators, not each of them. Remember, each of them, each of these JJ is not same as each of the JJ prime. I didn't prove that. I proved that the sum is equal. So each of them will be different, but total sum will be equal. And that is all I want in the Fock operator, because the Fock operator is a sum of the Coulomb operators. Okay. Now, quite trivially, you should be able to show that this also remains same. I will not do that exercise because this is nothing but this, except that there is a P12. Okay. So you should be able to prove this exactly the same manner, that the sum over all the Coulomb operators is identical. Right? Exchange operator is also identical. So the first point to establish that if I do unitary transformation, the spin orbitals remain orthonormal, the Fock operator remains invariant. That's very important. So I can immediately write the same Hartree-Fock equation by exactly the same way. F of 1, only this becomes chi I prime 1. So this becomes prime now, equal to sum over J lambda ij chi j prime, sorry, chi j prime 1. So exactly the same equation. I can write. You can say that this is also some lambda prime, doesn't matter. Some lambda prime, which we'll see what it is in the new basis. Okay? Because lambda will depend on chi, you will very quickly see. So I am calling it lambda ij prime. So this will be the Hartree-Fock equation in the new basis. I am not writing f prime. Remember, because I have just now showed that f prime is equal to f. So I have just now showed that f prime is equal to f. So if I transform the by spin orbitals by unitary transformation, the Fock operator remains invariant. Only the orbitals will change. So this change I have already taken care. So I am only now doing this change of the chi I. So, new chi I, I will get a new chi I. Now, you will very easily see why did I choose lambda as a lambda prime and what will happen to this, and this is where the canonicalization has a meaning. So, let me now